All right, so power series and radius of convergence. Now, power series sound kind of scary, but really we've been looking at them for a while now because Taylor and Maclaurin series are really just a subset of power series. Power series, the main thing about them, the distinctive characteristic, is they've got bigger and bigger powers of x. So if you look at this, which is sort of the generic infinite power series formula, we've got x, and there happens to be minus c there in case this thing's centered about someplace other than 0, as we saw with Taylor series. But the point is this n is in the exponent. So that means we're going to have powers of x all the way from x to the 0, which would just be a constant. So the first term of these things is almost always a constant, a sub 0. And then from then on, we'll have x to the first power, we'll have an x squared term, we'll have an x cubed term, we'll have an x to the fourth term. Or we might be missing some of these powers, like with sine and cosine, we only had either the even powers or the odd powers of x, because some of our coefficients were 0. But the point is that if you have an infinite series that keeps on going on and just higher and higher powers of x, that is going to be a power series. And of course, if c was not 0, then maybe instead of this, we'd have x minus c. And instead of x squared, we'd have x minus c squared. Instead of x cubed, we'd have x minus c cubed. But the point is, higher and higher powers of terms that have x in them is what's going to make this a power series. Now, why are we doing this? What's a radius of convergence? Well, basically the idea was, and we did this in the previous chapter, you could approximate something like, let's say you want to know e to the 0.1. And you know what e to the 0 is, it's just 1. So you wanted to use a power series or Maclaurin series to approximate e to the 0.1. You totally want to do that because it's totally relevant to your life and you're really curious what e to the 0.1 is and happen to not have batteries in your calculator or something. Anyway, the point is that if you wanted to find e to the 0.1, what you did was you built a Maclaurin power series centered at 0 because you figured 0 was pretty close to 0.1, and you cooked up this series that would approximate e to the 0.1 by plugging in 0.1. Actually, that would have been 0. We're going to plug in 0.1 for x. So when you want to approximate e to the 0.1, what you did is you plugged in 0.1 for x, and then because you were using e to the 0 is sort of like the point you knew that was kind of near 0.1, you plugged in 0 for c. So you centered it around 0. But the question is, how good an approximation is that? And more importantly, what if I wanted to find e to the 2.1? Do I have to start with a new series centered at 2? Like, do I have to plug in 2 for c? Or could I use my 0 expansion that I used, the same one I used for e to the 0.1? What about in e to the 8.1 or e to the 20.1? At what point does my Maclaurin series centered around 0 get bad enough I can't use it anymore? And more importantly, e is a pretty easy thing to approximate, but what if I was approximating sine x? Sine goes like this, right? It goes up and down, up and down. So if I created a Maclaurin series for sine, meaning I base it on this point and I sort of find a polynomial, the whole point of Maclaurin series is we're going to come up with a polynomial that sort of has a similar shape to the function we're trying to approximate. So when we do a Maclaurin polynomial for sine x, how good is it? If we did a third degree one, maybe it goes like this. If we did a fourth degree one, maybe it does this. If we did a fifth degree one, maybe it goes down and then up or something. But the point is that you can see how because the sine has that very distinctive up and down shape, it's going to be really tough to come up with a polynomial that sort of follows that indefinitely. So as long as we have a pretty good approximation, that's fine. But as soon as we go off shooting off into the yonder and totally miss the boat and totally miss a turn, at that point we're diverging from the thing we're trying to approximate. So the radius of convergence would be, hey, how close to our original point do we have to be to where this thing still works out? All right, so that's the idea of radius of convergence. Hopefully I didn't lose you. And now we're just going to show how to do the problems, because it turns out to not be too bad. Just as a reminder, the ratio test was one of the many tests for a couple of chapters ago about convergence and divergence of series. And the ratio test is going to be the one we use for this radius of convergence thing. So as a reminder, what you do is you just take a sub n is just whatever problem you're looking at, like n equals 0 to infinity of n factorial x to the n or something. A sub n is just going to be this formula exactly. And then a sub n is going to be this formula exactly. And then a sub n plus 1 is just going to be the same formula, except we'll stick in an n plus 1 for n. So no big deal. We just find that find that limit problem, and then as a reminder, if r equals 1, it was ambiguous, but if r was less than 1, the series converges. If r is greater than 1, the series diverges. So what we're going to do in this case is kind of do the ratio test backwards, as we'll see in a second. Instead of plugging in a bunch of stuff on the right and solving for r, we're just going to plug in 1 for r and then see what happens to the value of x that we can use. All right, so here's a basic one. N from 1 to infinity of x minus 1 to the n. Now, if you're sharp on these things, you might recognize this is a geometric series because we just have x minus c to the n power, and which means our first term is going to be x minus 1 to the 1. Then we'll have x minus 1 squared. So basically, we're going to have to multiply by x minus 1 to get to each of our next terms. But of course, that's pretty hard to spot. So what we'll do is just plug and chug through the ratio test and see what we get. We're guessing the radius is 1, though, radius convergence, because geometric series have a radii of convergence of 1. So just going to plug and chug through the ratio test. Limit as n approaches infinity of a sub n plus 1 over a sub n. So that's going to be limit as n approaches infinity of x minus 1 to the n plus 1 over x minus 1 to the n. This has a pretty straightforward formula, so it's pretty easy to plug and chug through here. So we're just going to get, and we want this to be equal or less than 1. But for a second, let's just simplify. So x minus 1 to the n plus 1 is just 1 higher power. So basically this x minus 1 to the n cancels that exponent, and we just get x minus 1. And since there is no n, we just get x minus 1. All right, so now the ratio test says that, hey, this thing would converge if whatever we get for the radius test is less than or equal to 1. So we need, and if the absolute value of that is less than 1. So if the absolute value of r is less than 1, I should say, not less than or equal to 1, is less than 1, then the series converges. So what we're going to do is, since we just found out that r equals x minus 1, we're just going to set x minus 1, absolute value of x minus 1, less than 1. And now we can solve for x. So how do you solve an absolute value like this? Well, the trick is just to get rid of the absolute value and figure, you know what, that has to be less than 1, but it has to be greater than negative 1. So now we can add 1 to all three. We get x is greater than 0 and less than 2, which basically means that the radius of convergence is going to be, the diameter of convergence would be from 0 to 2, therefore the radius is half that, which is 1. So r equals 1. That's kind of a different r. Should have said radius equals 1. Now you notice we didn't test the endpoints, and that's what we'll do in the next video about interval of convergence. But as far as radius convergence, we're just going to plug and chug through this ratio test process. All right, and this radius equaling 1 makes a lot of sense because, as we observed, this is a geometric series. In geometric series, as long as the r, the thing you're multiplying, or the common ratio that you're multiplying by to get from term to term, as long as r is less than 1, then the thing converges. So it makes sense that we need these terms to get smaller and smaller. So as long as x minus 1 was between negative 1 and 1, then the higher the exponent you raise it to, the smaller the term gets, and therefore it makes sense it would converge. All right, here's another one. Now you can see this one's a little bit more complicated, like the formula is more complicated. So we really do need to use a ratio test. We might not be able to guess at this one. Right off the bat, we'll have to plug and chug through the ratio test. All right, so once again, by the ratio test, let's take n approaches infinity of a to n plus 1 over a sub n. All right, so a sub n plus 1 is going to be n plus 1 factorial times x to the n plus 1. Then the denominator is just plugging in n, so we get n factorial and x to the n. All right, so if you've seen the ratio test video recently, you'll realize some stuff cancels pretty nicely here. But I will just expand it a little bit for you. So n plus 1 factorial is going to simplify to n plus 1 times n factorial. And the idea is that with a factorial, like n factorial, is really n times n minus 1 times n minus 2 times n minus 3, dot, 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 all the way down to 1. So if you're starting at n plus 1 as your first term, then your next one is 1 less than that, and 1 less than n plus 1 is just n. So that's why n plus 1 factorial is just n plus 1 times n factorial. And the reason we like to do that is because that will cancel the n factorial from downstairs. So this n factorial cancels that, leaving just the original n plus 1. And then x to the n plus 1 and x to the n. The power upstairs is just 1 bigger than downstairs. So this cancels this, and we just end up with x to the 1 upstairs. All right, so the limit as n approaches infinity of this ratio test thing is n plus 1 times x. So what is wrong with this picture? What does this mean for our interval of our radius of convergence? Well, it's kind of a problem because if you plug in, if n is approaching infinity, and n is in the numerator here, it's just n plus 1. So it really doesn't matter what you plug in for x. If n is approaching infinity, n plus 1 is approaching infinity. If you plug in 2 for x, 3 for x, 10 for x, then obviously 10 times infinity or whatever is going to be 0. Even if you plug in a really tiny number like 1/100th, 0.01, 0.01 times infinity is still infinity. So no matter how close you put x to 0, this thing is not going to converge because any number times infinity is still infinity. There's one exception. There's one number we could plug in for x, and that number is 0. So if we plug in 0, this thing converges. But that's not real exciting, is it? Because this original series was centered around 0. I know that because it's got x to the n. If it had x minus c to the n, then it'd be centered around c. But since it's just x to the n, that means there must have been c must have been 0. So basically they're saying, you know what, this thing converges for the one value we knew, but then if you try and approximate anything besides that number with this series, you get infinity, so it doesn't work. So basically this is saying, you know what, you just can't use this series to approximate this function, your kind of host. And you might say radius equals 0, because there is no radius convergence. It turns out that for a power series, it never diverges for everything. 0 always works. Or if it's an x minus c series, then c will always work. Because if you plug in c for x, you get c minus c to the n, and c minus c is 0. So the same thing happens. As long as you have 0 raised to the n power, like infinity or something, then your terms will all be 0, so it converges. All right, let's take a crack at another one. This one looks kind of gnarly, but once again, we're just going to plug and chug through the ratio test, and everything should work out if we don't mess it up. All right, so the ratio test, we got limit as n approaches infinity. The top is going to be -1. You know what? I'm actually just going to ignore the -1. Why is that? Because the -1 is just going to make it alternate, but that's not really what the ratio test is all about. Alternating series have their own test, which is basically if the terms are getting smaller and smaller and it alternates, then it works. But for this particular type of problem where we're solving for x and to find the radius and convergence, we don't need to worry about the alternating. When we find the interval of convergence, that -1 will go back to playing a role. But for now, we can just do the ratio test, which ignores the plus or minus sign, the alternating aspect. All right, so I've got x to the, we need a sub n plus 1 up top. So that's x to the 2 times n plus 1 over 2 times n plus 1 factorial. And that's going to be over x to the 2n over 2n factorial. And you kind of need to put the 2n in parentheses because 2 times n factorial is very different than 2n factorial. So two different things. In this one you would take n factorial and then multiply by 2. But in this one you're starting at twice as high a number. So 2n in parentheses factorial is way bigger than 2 times n factorial. All right, so At this point, we just have a lot of parentheses to work out, so limit n approaches to infinity. So up top, we have x to the 2n plus 2. And down here, we have 2n plus 2 factorial over x to the 2n and 2n factorial. All right, so this is only a little bit different than the previous problems we worked. So we've got these 2's in here in front of the n. So x to the 2n is going to cancel x to the 2n, but there's still x squared left over. So I've got x squared. And then 2n plus 2 factorial is going to be 2n plus 2 times 1 less than that, that's 2n plus 1, times 2n factorial. And then down here we still have a 1, and then a 2n factorial. So this is going to cancel this, but we're still left with that 2n plus 2 and 2n plus 1. All right, so at this point, everything's reduced, and this is what's left of our problem. So we need to take the limit of that as n approaches infinity. And so the question is, what can we plug in for x that would make this equal to 1? So we need x squared over 2n plus 2 times 2n plus 1. So we need the limit of all this to be less than 1. Well, it turns out that you can actually put in anything you want for x, and it'll come out okay. Because as n approaches infinity, remember it's n approaching infinity, and the n's are all downstairs. There's an n in this term, there's an n in this term. So the denominator is approaching infinity squared, essentially. And we've got infinity times infinity downstairs. And upstairs, we just have a constant. No matter what x is, 0.1, 5, 25, 100, any constant we plug in for x, that's just going to be a constant. It's not growing because n's approaching infinity. X is just the number we're trying to solve for. So even if we plugged in 1,000 for x, and 1,000 squared would be 1,000,000, regardless, when you divide 1,000,000 by infinity squared, the thing still approaches 0. So it turns out that x can be anything, from negative infinity to positive infinity, and this thing will converge. So the interval of convergence is negative infinity to infinity, or another way of saying that is that r equals infinity. The radius equals infinity because no matter how far you go to the right or left, the thing will converge. All right, so here's another one, which appears to be pretty much the harmonic series with a tweak because we have n to the first power downstairs, but let's take a crack. So first thing we do is just to set up the ratio test. So we need, and again, we're going to ignore the -1 alternating aspect right now. So we need a sub n plus 1, so that'll be x to the n plus 1 over n plus 1 divided by x to the n over n. So x to the n cancels this, and we just end up with x to the 1 upstairs. And we can't really cancel the n's quite, so let's just rewrite this as n approaches infinity. So we've got x, and if we invert and multiply the denominator, because we basically are dividing by 1 over n, so we've got x times n over n plus 1 after we sort of condense these fractions. Now the question is, what happens as n approaches infinity? Well, because we want to solve for the x that would make this less than or equal to 1, right? This fraction. So as n approaches infinity, n over n plus 1 is going to approach 1. And to help you see that, what we could do, this x is technically a constant because it's not n. If you look at this limit problem, n is the thing that's approaching infinity. N is sort of the variable for this particular limit problem. And remember, when there's constants in a limit problem, you can just move them out front. It's no big deal. We're not used to thinking of x as a constant. But in the case of this problem, it is because n is the thing that's approaching infinity. X, nothing's happening to it. We're trying to figure out what constants we could plug in for x. So in that sense, x is basically a constant for this limit problem. So what we can do is we can rewrite the limit problem with x out front to help us see what the limit would actually be. And this thing, hopefully you can see now, is just 1 because by L'Hopital's rule or any other way you want to look at this, this limit is just 1. So for this series to converge, we basically need this thing, which is x, to be less than 1. And you can see right away that x is less than 1. Now you might be wondering why I didn't use the absolute value signs again. And technically I could. The thing about radius of convergence is that it's always symmetrical. So if you just make x less than 1, technically that doesn't, normally if you said x is less than 1, then -5 would work and negative infinity would work. But what I kind of mean here is that the absolute value of x is less than 1, meaning that the radius of curvature is 1. Technically, we've got x is less than 1 or greater than -1, but the point is the radius curvature is 1. All right, last one. So once again, if they mention radius convergence, you basically don't even need to think. You just go straight to the limit problem. So limit is n approaches infinity. So we want to plug in n plus 1 first. So we got n x to the n plus 1 over n plus 1 factorial over x to the n over n factorial. All right, so that's the limit as n approaches infinity. My arrows need work pretty bad. All right, so we got x to the n plus 1. Now n plus 1 factorial, as we've seen before, you just want to change that to n plus 1 times n factorial. You get x to the n and n factorial. All right, so the n factorials cancel. Then x to the n cancels this, except for the x to the 1. So we end up with the limit as n approaches infinity of x over n plus 1. All right, so what's the deal here? Well, as n approaches infinity, once again, we've got an x and we've got an n, so what we could do is just move the x out front. So it'll be x times the limit as n approaches infinity of 1 over n plus 1. And remember, I want all this to be less than 1, because the ratio test tells you the series converges if r, the ratio, is less than 1. Or technically, you want the absolute value of this to be less than 1. But the point is here that the limit of 1 over n as n approaches infinity, this is just 0, which means 0 times x needs to be less than 1. And of course, it wouldn't matter what x is. X could actually be infinity. Infinity times 0 is 0, which is less than 1. So it turns out the radius for this one is infinity. And if you just like logically, because you want to sort of be able to, once you practice these enough, you'll start to get some intuition about what converges and what doesn't converge. And basically what we're saying is it doesn't matter what you plug in for x, this thing will still converge. And the reason for that is that n gets really, really, really big, right? N goes to infinity. So even if you had x equals 1,000, which is obviously a pretty big number, 1,000 squared, 1,000 cubed is pretty big. And at first the terms would be ridiculously large, because 1,000 cubed over 3 factorial is a huge number. It's close to 1 billion. But once you get up to n's on the order of 1,000, then we've got 1,000 to the 1,000, which looks pretty bad, except downstairs you've got 1,000 factorial. So that's 1,000 times 999 times 998 forever. And you can start seeing how this denominator is actually getting into the ballpark of size that the numerator is. Because upstairs you have 1,000 thousands. Downstairs you have a lot of numbers also. And once we get up to 10,000 or 100,000, then the denominator actually starts getting bigger than the numerator pretty fast. All right, so the moral of the story here is that this is basically 1 over n factorial, and that since x is a constant, it almost doesn't matter what number you raise it to, it's still going to get outpaced by factorials, because factorials just get really, really big. All right, so if you don't get this stuff so far, don't worry about it. In the next video about interval of convergence, we're basically going to work some more problems exactly like this, except we'll just add a step onto it, which is testing the endpoints. Because at this point, it wasn't true on this problem because radius was infinity. But if we got a radius equal to 1, and we're centered around 0, so let's say that we know that x needs to be less than 1 and greater than -1, that's all fine and dandy, but what about 1? Could I plug in 1 and it would work? Or if I plugged in 1, would it diverge? Same thing for -1. You're going to be asked to test not only what the radius of convergence is, but how the thing acts at the endpoints. And that's just the one extra step we're going to tack on when we find the interval of convergence in the next videos.